Hi, my name is Chloe Metz, and this is Group 14's final video for the CBE 330 challenge problem. So, as well as pictures of our pets, please enjoy Tibia or Not Tibia, that is the model.
We decided that we were going to be modeling the rate of bone growth after different age groups experience a transverse tibia fracture. We decided that we were going to model different age groups so that we could better understand how bones change speed in relation to their age. Specifically, we decided to focus on the data for a child and for an adult. We also focused on the tibia because it deals with a bone that has a lot of stress on it and it is commonly broken. After you do get that fracture, there are 5 steps to the bone healing process. The first step is blood clot formation, and it lasts for that first week. Then you get inflammation, which lasts for that second week. The third step is soft callus formation, and it lasts for that third week. And then it immediately goes into a hard callus formation, which lasts from that third week to that 6th week. And the last step is bone remodeling, and that can last for up to a few months. We decided that we were going to be focusing on the callus formation parts of these steps. That includes the soft callus and that hard callus. For the soft callus formation, you have mesenchymal stem cells, and it breaks into 2 groups: cells that are forming cartilage and cells that are forming bone. The product of this step is fibrocartilage and collagen. And then we immediately go into the hard callus step. This step, once it starts, immediately stops that soft callus formation because it is taking the products of that soft callus and mineralizing it. This means that we are taking it and turning it from cartilage to bone. To model the callus formation in our problem, we decided to use an initial value problem and a coupled set of ODEs. We decided to focus on this as our problem so that we could develop a better understanding of how the bone naturally regrows and focus more specifically on how it changes in speed with different age groups.
For this project, we had to define some constants, assumptions, and simplifications. First, we decided that both age groups suffered a mid-shaft transverse tibial fracture with a 1 mm defect. This can be seen in this left image here. Other than this fracture, both age groups were the same gender, otherwise healthy, and had similar diets and environments. This is so that they would heal similarly. Total callus formation and hard callus formation / mineralization could also be added together to find the total bone formation. Like Olivia described in the last slides, bone regeneration can be very complex and there's a lot of factors that contribute to it. So since we're not experts, we wanted to specifically focus on callus formation. For our methods and theories, we first came up with this first equation, which comes from our last assumption. Again, we are assuming that soft callus and hard callus will add up to be the total bone density. We can see here that they're all functions of time, and therefore it will initially start at 0 when bone initially breaks, which helps us come to our initial conditions we'll define later. But how do we find these different callus densities? This is where equations 2 and 3 come in, which are both ODEs. Equation 2 shows the rate of soft callus formation, while equation 3 shows the rate of hard callus formation. These 2 equations are almost the same with just a few key differences. K1 or K2 are the rate to show how fast a callus is being formed. K1 would be constant, while K2 would not. K2 is found with equation 4, which we'll get to in a minute. Rho S max and rho H max also are constants, which represents the max bone density when the bone is fully healed. These values were approximated by taking into account the amount of time it takes for soft callus to form in different age groups. In equation 2, there is a subtracted term that is later added in equation 3. This term shows the formation of soft callus turning into hard callus. So we subtracted it in this equation 2 and add it back in equation 3. For equation 4, it's the rate of soft callus formation turning into hard callus. Equation 4 shows that the rate of soft callus turning into hard callus, K2, will decrease with time. This conceptually makes sense since the bone will heal, the gap between the break will decrease, and callus formation will happen. L represents the length of the break. Here we assumed it to be 1 mm, and D represents the medial lateral diameter of the bone, which would be different in age groups. K2 represents the initial rate of mineralization that was estimated. Now that we have 4 equations, we can be solved using ODE solver and initial conditions in MATLAB. Initial additions were equation 5, are found by assuming that when the subjects rate their bone at t equals 0, there will be no soft or hard callus present.
For our model, we have a system of two coupled ODEs, since the equation for hard callus density depends explicitly on the equation for soft callus density. The hard callus formation depends on soft callus, but the soft callus is independent, so the system is only one-way coupled. The hard callus is formed by both direct mineralization and, as time goes on, the soft callus converts and mineralizes into the hard callus as well. This model uses the ODE 45 from MATLAB to solve the system. It is a Runge-Kutta-based operation within MATLAB that can effectively solve non-stiff, explicit, low-dimensional functions. The Runge-Kutta method uses a ODE 45 specifically uses a fourth order and fifth order method together to increase accuracy and reduce error. The Runge-Kutta method uses multiple trial slopes at different points during each step, totaling 6 intermediate slope calculations per step that are combined into a weighted average to give the value. This model also takes into account the geometric regulatory factor relating the length and diameter of the bone and the breakage for both the child and adult, which gives a regulating factor to the equations, leading to longer bones taking longer to heal, with children, as you can see in the graph, healing faster than adults and having calluses form, both soft and hard, quicker than adults, but stabling at the same rate.
As Sean explained, when we compare the healing curves for children and adults, the difference is very clear. By around 100 days, the child reaches a total density of about 83%, while the adult is only at about 64%. A lot of this comes from how the callus types behave. The soft callus, which is the early scaffolding, forms faster in children and gives an early advantage for the hard callus phase. So not only do kids build the initial structure sooner, but they also convert it into fully mineralized bone more efficiently. Overall, our model shows why children tend to heal noticeably quicker than adults. As a part of assessing the reliability of our model, we examined how sensitive the predictions were to the estimated parameter K20, which represents the initial rate of mineralization of the soft callus into hard bone. Overall, even when we scaled K20 up by a factor of 100, the final density only changed about 0.0044 for the child and 0.00015 for the adult, which is a very small number. Overall, this tells us that the model is very stable with respect to this parameter, and even if we had errors in our K20, which, as we estimated, we probably did, there should be no significant effect of that on the predicted healing outcomes. For our model, we kept things pretty simplified. We didn't account for any real-world factors like diet, physical activity, mechanical stress on the bone, or any underlying medical conditions, all of which would influence healing time. We also only compared a typical child and adult, so the model doesn't include older populations or any sex-based differences. We were also limited by the amount of human data available on tibia healing, making it harder to specifically detail the model as much as we wanted to. Overall, our model could be improved in a number of ways, such as by adding more variability of the parameters, expanding the age range, comparing male and female differences, and even using animal data where the research is more complete. And that is our presentation, so thank you so much for watching.